Hello, welcome to this video. I'm going to be talking about Word2Vec. Now, before I talk about Word2Vec, let me start off with a simple corpus and something called count-based embeddings. Now, we've got this corpus with three sentences, and we can map it to something called a co-occurrence matrix, where words appear together. Now, we see math and technical, statistics and technical, and history and narrative that appear together. So by looking at this matrix a little bit carefully, we can see that there are two major problems that occur with count-based embeddings. First, it doesn't capture semantic meaning, right? Math and statistics are clearly related. Second, there are a lot of sparse vectors. We've got a lot of zeros and just one entry. So let me talk about these two problems a bit more in detail. In a count-based system, the vector for math and statistics are mathematically as different as math and banana. Their similarity score is 0, therefore failing to capture semantic meaning. So if it doesn't co-occur together, it's basically the same as saying math and banana, which doesn't make that much sense. The model can't generalize. If it learns something about math, it can't apply that knowledge to statistics because it doesn't realize they are related. Now here are two sparse vectors with the and a located in it, with entries from 1 to 100,000. So if the number of rows is equal to 100,000 and you use a 4-byte floating point number for each entry, a single word vector takes 400 kilobytes. To store the entire vocabulary matrix, V times V, you need 40 gigabytes of RAM just to hold the table. So with respect to the dot product, you're asking the CPU or GPU to perform 100,000 multiplications. But because 99.9% of the values are 0, the result is almost always 0. You're burning clock cycles on multiplying by 0, which is a massive waste of throughput. This is a data science bottleneck called the curse of dimensionality. In a 100,000 dimension space, data points words are so far apart that the model requires a near infinite amount of text to find meaningful patterns. And then there's the zero frequency issue. If statistics and math never appear in the exact same sentence in your training data, their count-based correlation is exactly 0. So Word2Vec was developed by a team at Google in 2013. It's a technique in natural language processing that uses shallow two-layer neural network to turn words into numbers, specifically dense vectors of floating point numbers. There are two possible ways to train Word2Vec embeddings. One, the skipgram approach predicts the context of words from a word of interest. The continuous bag of words approach predicts the target word, the output word, from nearby words, input words. We'll be looking specifically at the skipgram approach. Now here's an example, a sentence example. Machine learning provides a computational framework for applying statistical models to vast data sets. So we've got framework, which is WT, and computational, which is WT minus 1, and provides as WT minus 2 because it goes before framework. Now after framework, you've got WT plus 1, which is 4, and WT plus 2, which is applying. So we could break the sentence down basically and put it vertically just to illustrate what I'm trying to show you with the skipgram approach. It basically is a sliding window approach where we use the word as a input, which will later map to a one-hot encoding. So the first thing we look at is that we've got WT computational, WT plus 1 framework, and T minus 1 provides, right? I'm going to use a lag of 1, minus 1, and plus 1 to simplify. I'm not going to use WT plus 2 and WT minus 2. So computational would be the 1 and everything else would be 0 as our input. Then we would use framework as the input, and the surrounding words would be computational and 4. Four would be the input, and the context words would be framework and applying. And we could go down the list to 2 vast data sets, right? WT would be vast, WT minus 1 is 2, WT plus 1 data sets. Now I'm going to be talking about the skipgram architecture and how we get to basically probabilities for words. Now, I've got the sentence, but I throw in a little bit of a problem into our sentence, and that's a good old cat, okay? The reason why I throw that in is that we consider that word as somewhat of a negative sample, right? Negative sampling, right? Where we put in a word so ridiculous and we test out our algorithm to see that if it's classifying the words we want versus the ridiculous words. Now, if it predicts or it weights the ridiculous word, which is cat, in our example heavily, then we know we've got a mistake, okay? Another thing I want to make, a point I want to make is that it should be bidirectional. So if we use computational as the input, it should be able to predict whether it provides backwards or framework forwards, okay? So I do want to make that important point. One more important point is that in our first initial run, we're going to be using random values. Because we're using random values, something like cat could be close to computational when it's not, right? Because we're just throwing in the initialization phase, we're just randomizing it, okay? So I do want you to keep that in mind. Now I show this as computational and I set it to 1. We've got this random dense vector representation now, right? We don't have the zeros and the ones anymore, okay? And that's done by the embedding matrix, okay? So we do a 1 by V, which is a one hot encoding. v by n, and we multiply that out. So we get a 1 by n matrix, which is the hidden layer, right? And we also have a context matrix, and this also was randomly initialized. And we've got cat in there, which is close to computational instead of provides. If we do a dot product, we take the hidden layer 1 by n and then multiply n by v, we'll get a 1 by v of logits. If we apply the softmax function on the logits, we're going to get some probabilities. Now, the target were provides and framework, but instead we got the bulk of the probability weighted towards cat. And this is clearly an error, right? And the cross-entropy should be able to pick up on that. So it'll pick up a large error, say 0.99, right? I'm just making that number up. And it provides, cat has a large dot product with computational, right? Not provides. So that has a high, cat has a high dot product with computational, right? We could see that from our embeddings, right? These were, remember, randomly initialized. Computational and framework has a low dot product, right? A low occurrence probability. So we could use stochastic gradient descent, and it nudges computational and framework to be pulled closer together. So you could see that those two dense vector embeddings are closer together as a result of stochastic gradient descent. While cat dot product with computational is decreased. Okay, so we see that when what stochastic gradient descent does is that it pushes them apart with respect to value. Now you could see that because of that, the framework has a higher probability weight, and cat, the probability weight is decreased. Now this lowers the cross entropy, and as a result, the loss improves. So in the last iteration, we started with computational is equal to 1. And we would do the following. We would do what we saw earlier. We'd set framework is equal to 1 in this case, and it would slide, right? The new target would be 4 and computational, right? Because it's bi-directional. and we would slide again. And we would slide again, and we'd iterate until cross entropy loss across the entire data set has reached its lowest possible point. So we're minimizing cross entropy, and that's the goal of this algorithm. Now, I do want to make an important point. In a larger dimensional matrix example, applying softmax can be computationally expensive because it is applied to each row. In our previous example, we just showed a general case. So the idea was just to see the process, right? So we would have softmax applied basically to each row in this multi-class classification problem, right? We'd have one, a probability that probably gets away weight 0.550, for example, and then the rest of them 0.001. And that's a lot of computation. So instead of using that, we're going to use a logistic regression with negative sampling. Now here's the skip architecture with logistic regression and negative sampling, right? From the beginning, I use a different example. I use machine and then learning. And then I use some negative sampling words like banana, sky, and table. If we look at this example, machine and learning, okay, are pretty close together, okay? We see the hidden layer, the content matrix, and we do the dot product, right? And we get a logit of 2.8. We apply the sigmoid function to 2.8 and we get probabilities of 0.94 and 0.06. Now you see that the output probabilities have become bivariate instead of multivariate, right? We've got two outcomes. And that's what skipgram with negative sampling should be doing with logistic regression, right? It should be sliding so that we get bivariate outcomes instead of having all these fillers, okay? And it'll slide, right? And it'll classify whether it's close, machine learning is close, or it's not, right? If, of course, machine and learning is close in this example. So it reduces the computation. Now you could see in this example, machine and banana are basically more pushed apart, okay? And that's because of stochastic gradient descent. If we go look at the logit, it's a negative 1.5, right? And then negative 1.5, the sigmoid is 0.26, okay? And the rest would be 0.74, okay? So the idea is that learning is pulled towards machine and banana is pushed away from machine, okay? And that would minimize the binary cross entropy loss, right? And then that for that iteration. So we saw a simple representation of Word2Vec. Word2Vec is usually represented in 100 to 300 dimensional space. We can collapse a high dimensional space into three-dimensional space using something called principal components analysis. Now, I use the word mathematics as the word I'm interested in, and you could see that there are a lot of words circling around it that have some type of semantic relationship. So mathematics and physics, mathematics and abstract could go together, right? Mathematics and theorems, mathematics and axioms, which are ideas used in the branch of mathematics. But you could also see at that angle where it's a right angle, the blue, that there's a word called literature. And that would be probably the opposite of mathematics. It definitely wouldn't be related. So it would probably have a lower dot product. Thanks for watching.